So let's see where we stand right now. So part one was about, let me give you a very simple algorithm that might have problem in high dimensions, but give me the opportunity to show the bias variance trade-off, so which is the basic idea behind parameter tuning, which is the problem in most machine learning, or one of the biggest problems in most machine learning. This is cross validation, and then essentially looking a bit at dimensionality as a motivation. We moved from local method to global methods, introduced linear models, the computation for linear models in the least squares framework, and then now I'm to dictionaries and kernels, and as a way to move away from linear modeling to something more complicated. Okay, my little sketch here when I do this. When I do this, I'm aware that it looks like a shameless trick, okay? And that's kind of how I want to present it to you, okay? Because the theory of this stuff is actually pretty big. What I wanted to point out is mostly, like, believe me and check that you can do it, because you can run the code and see how it works, okay? And just appreciate how you can use it. The math behind this is actually very nice, but it really would require like an hour just by itself. In the course we do it on me in the fall, I think we have 3 hours on this, and they're not right now, so it's long. And I just talk about the first item, don't even talk about the last week. So this, I'm okay if you see it kind of as a trick, and if you don't believe me, just try on the data today and get it code and see how it works in practice, and kind of convince yourself it does the job. One thing I didn't mention here, which might be interesting, is that, again, there is this big problem how you choose the kernels, and that there is a whole lot of literature here related to kernel learning and multiple kernel learning. So how you can, instead of one, you can mix more than one kernel, how you can learn one kernel out of a set of kernels, and so on. Again, it was kind of variation over this theme. You have to add on top of this, okay? But you don't have to start from scratch. Is there any question about this first couple of parts? So the last section somewhat has a slightly different flavor. The first part is something very recent. This one I'm telling you now is something very old. And I'm just showing it to you now because I think it's I don't know, I like it, it's refreshing, and it's still one of the main building blocks for many complications. If you understand that right, you can use it to develop a lot of different solutions. Both these two topics, variable selection, OMP stands for orthogonal matching pursuit, or matching pursuit is the one algorithm I'm going to tell you about, and dimensionality reduction and PCA are basically somewhat related, at least in my view, which is biased by the kind of machine learning application I have in mind. They move away from black box kind of approaches where you basically say, I just want to make a prediction, and I want the prediction to be good. I don't want to know how you make the predictions, but just make good predictions. Okay? They move away from this into a slightly more exploratory world where you say, I want to get a good prediction, but I also want you to tell me how you made them. Okay? And I want to understand more about the data. There are a lot of applications around now where this has become the questions. Okay? Maybe if you want to recognize faces, you don't really care, you just want to do well. Okay? But a lot of applications, especially in biology, this is kind of perhaps a bit outdated, because just to make a point, are really like that. So this is the application, this is a classical problem. Is there any of you working on genomic data? So this was a classical example. So this is supposedly you have a bunch of patients, okay, and you have disease type 1 and disease type 2. One is much more aggressive than the other. And so when a patient arrives, you want to check whether it's type 1 or type 2 to treat him the best possible way. Say, this is, for now, I think it's kind of a dream, but that's kind of what the story is. The patient arrives, and you take a sample of, say, a tissue, and then what you produce is this kind of stuff here. This is what was called the microarray, which basically gives you the expression of each gene in the DNA of the person, in the affected region, okay? So basically, this is literally an image, and you can unroll it into a big vector, okay? P here is, roughly speaking, the number of genes in the DNA, and each number, X1, is the expression of the first gene in the first person. And these are just first person, second person, and so on and so forth. Okay? So it's just another instance of the problem I showed you before. Before there was faces, now is patients and their genes. Okay? Let's say that this is, again, plus minus 1, type 1, type 2. And so one question is, again, I give you the patient, give me a rule that given new patient is going to tell me what is going to be more likely type 1, type 2. Okay? But a lot of times when you go to a doctor, actually, if you give him this rule, he just doesn't believe it. Okay? Especially when people in clinics, they're like, all right, how did you do that? You say, well, I have a supervector machine. They're like, right. And then they ask you, okay, which kind of information did you look at? Because I want to check it out. I want to go and check and double check that that gene is actually important. So they typically ask you a list of genes. Okay? They want to know which genes are important for what. One reason for, because they want it, perhaps they don't trust the black magic of statistics and machine learning. But another reason is, for example, that these measurements are awful. Okay? They're borderline reproducible. Maybe they're a bit better now, but at the time when I would look into this kind of stuff, if you do the same experiments twice, the amount of variability was ginormous. So what they wanted to do is, if I tell you that this one gene is very important, I'm going to go in, check with another kind of technology, which is it's more expensive. So I cannot do it for 20,000 genes, but I can do it for 5, 10, 20. And I'm really going to get much more careful measurement, and then I'm going to check if this guy was really active. Because maybe here it looks like it was active, but it was not. Maybe this bunch of microarray had just some bias, okay? So they typically want to know which variables, which genes, which of these columns were important to actually make this decision, okay? And they want to make the prediction. Importance here is importance as with respect to make predictions, okay? But the two questions are slightly different. And one way to see it is they want an interpretable model. They just don't want to make prediction. They want a little bit more, okay? How do you solve this problem? So turns out that the problem is classical in statistics, and it's called variable or subset selection. And the simplest way to do this is to just assume the model we'll be assuming so far, the linear model. Notice that now, so this is just a unroll it. These are weights, and these are exactly, say, if this is patient 1, these are going to be his gene expression, okay? And those measurements do matter for us, okay? We want to know which of those. We don't want to combine them. We don't want to put them in high dimension. We know which of those is important, okay? And the way we think of importance here is if the associated W is big, then this is important. If it's not important, okay? So we kind of look a bit into this, and we basically say, to say if a person is going to likely to be sick or not, we're going to look at this gene expression and weight them and let them somewhat vote for whether this guy is important or not, and somewhat the weight of the vote is related to this quantity, okay? So this is the other definition of variable selection, which is in a classical book. And this is kind of, well, I like it. And they kind of point out one point, which is, this is a hard problem. It's a harder problem, okay? Detecting which variables are important is a much harder problem. And so one new thing in the last few years that we start to have kind of clean protocols and way of doing, which are provably effective at least under certain conditions and efficient. Okay? Whereas until 5-10 years ago, it was basically just a series of heuristic techniques that would not be come with guarantees. And it's easy when you have no guidance in such a hard problem. And imagine to just fool yourself in believing that you find the question. Again, the classical case of this was the one where you had something like, I don't know, tens of patients at most, and thousands, tens of thousands. 2, 3, 4 tens of thousands of genes, okay? So in some sense, we have a very, very high-dimensional problem, and there is no sparsity in this matrix. It's a dense matrix. It's a big, fat, dense matrix, okay? So how do you do that? So the keyword entered the picture is sparsity. Okay? How many of you know what sparsity means in this context? Good enough? Basically, we say that this function or this vector is sparse if some of the coefficients are 0. Okay? The sparsity level is how many coefficients are not 0. So the game now is going to be, okay, I'm hoping that the best possible function that allow me to predict whether a person is going to be sick or not is going to be sparse. So that I don't actually have to look at all the possible genes, but I just have to look at a subset of them. Okay? It's a prior. Okay, we hope it's true, and we try to enforce it, and we check, and we try to enforce this kind of assumption.
So
yes.
Sparsity with respect to the weights, or the
yes, the weights. So you take each is a gene measurement, and then you say if the associated weight is 0, then it doesn't matter. And this is specific for each input, but this is just for any possible input. So whenever you find that, you get a new input, and if it's this WJ is 0, you will never look at that measurement at all. Okay? So there are some diseases that turns out to be controlled by a handful of genes, like 1, 2, 3. There are other where you have complicated pathways and processes that are not just reduced to 1, 3, 4. But this is also something you can study. Okay, so I'm starting to be burnt out. So now you help me out. Suppose that I give you an infinite computational power. Okay, so let's not worry about computation for a second. You have an infinite computer, and now you want to solve the problem. How would you do it? Suppose you can run least squares on an infinite.
All possible combinations of variables and run and choose the best one.
Right. So you just said take all possible combination of variables, and so I would say take all individual variables and say run regularized least squares, for example, or just least squares. And you take all couples, and you take all triples, and just keep on going, okay? And clearly this, well, I'm not sure about clearly, but one can prove this is actually optimal. If there is a sparse solution to the above problem, you're going to get it, okay? But clearly this is combinatorially explosive, and you get completely unfeasible even dimension. I think you might go up to dimension 5 or 10 in some tricks, but die pretty soon, okay? And this is kind of the brute force approach. You try all possible combination, and it turns out that this can be actually written in this way. So as a least square problem, where this SW is just a linear function, and this is the so-called zero norm. Basically, it's not really a norm, and it just counts the number of coefficients which are different from 0. Okay, so you give me a vector, and the zero norm of the vector is how many Wj are different from 0 in that vector. Okay? It's just good to know that it exists for what we're concerned right now. And the other thing it's good to know is that the non-feasibility of the problem is essentially a consequence of the fact that this norm, one can show it's not a convex function of W. Okay? So this is a non-convex problem, and associated, so it cannot be solved, and it turns out that it cannot be solved in polynomial. Okay? So essentially, once you are fine accepting, and nobody complained, but you should have, a linear model, okay? If you're willing to accept a linear model, then you know that you could approach the problem this way in theory, but you cannot do it in practice. And the problem becomes, can we find practical approaches for which we can try to find an approximate solution, and then ideally derive some kind of guarantee that tells you how good the solution is, okay? So how would you do it? You cannot try all possible combinations, so how would you do it?
Could you fit normally and start cutting off weights that seem to be below a certain threshold?
So, but I guess what one possibility is do least squares, like the one I showed you before, the linear least squares, fit the best way you can, and then you already have a lambda, and then you put another parameter that would be some kind of threshold, and basically you say, I get the W vector of my linear model, and I look at each entry, and if it's small, I throw it away. And then I have to decide what's small. And now I have two values, okay? Yeah, so that's kind of one way of doing it, and I'm going to try to point it out in a second. It's kind of hard to prove anything about this, and you have two parameters. Okay? You have a parameter, in some sense you have this one parameter that controls the stability of the problem, then there's other parameter that controls how many coefficients you want to throw away, and it's not completely clear how they interact. So for example, one question is, do they do a similar thing? Why did you put the stability one to be sure that you were not fitting too much? Maybe it's the case that the other one you put is also doing the same thing.
Well, that was going to be the other idea, is possibly putting a prior on the parameters that shrinks them towards zero, so large ones.
Right. And this is one approach, okay? And it's exactly the approach I'm not going to talk about. I'll show it to you. So basically, remember that somewhat a very flattering way to look at this from a probabilistic point of view is basically put an exponential here instead of a min to the max. Exponential to the minus, okay? And then this is basically the prior. If you just find not with probabilistic prior, you can think of this still as a prior. And so what he just said is, can you put a prior that is going to force the coefficients to be zero? Notice that when you look at Tikhonov, it's kind of doing something like that, okay? Because he's saying that you want to look at something like this, and this is just Wj squared, okay? So when you look at Tikhonov, you're basically saying, I want this thing to be small, and so this is basically I'm putting a budget on my W. The main point is that you can check, and I'm not going to give you an explanation of this, that most of the things will be actually different from zero. So you do a shrinkage, but you don't make them zero. You just make them small, okay? And then you do have to further threshold. So the question is, can I actually make them zero, like this would do? Okay, the zero norm, the zero prior would do. And it turns out that yes, you can do it. Okay, and there are a bunch of different ways to show it. You basically have to replace this zero norm, not with the squared norm like this, but with the L1 norm, which is the sum of the absolute value of the coefficient. And it turns out that one can prove a couple of things. One is this actually does shrink the coefficients to be exactly zero. Okay, how much zero depends on lambda. If lambda is very big, most of the coefficients will be zero. If lambda is small, you're just fitting and you don't care. The other cool thing is that this is actually, when you replace the zero norm with the one norm, the problem you get is convex. So people describe this operation as a convex relaxation of the original problem. It's not strictly convex, so it might have a flat region. It's not just a nice smile. It's like you have flat region, so there might be more than one minimizer, but it is convex, and so it's not computationally unfeasible anymore. And there are really a lot of methods, and in the last few years, a class of first-order methods called proximal methods, soft thresholding method, emerged as one of the best ways of doing this because they're simple and they do scale for very large data sets. These have different names because introduced kind of in signal processing and in statistics around the same time, 95 and 96, sometimes called basis pursuit in signal processing or lasso, suit maybe, in statistics. It's kind of one of the biggest topics, it's beaten down to death in the last few years. They've been studying all possible flavors, and it turned out that this is something that people in, I guess, use statistics. I don't know. Anyway, people have been doing this kind of stuff from a practical point since forever, since the late 70s and perhaps even before. Ben Logan is the kind of the name that people mention every once in a while, being one of the pioneers on this. The other thing, this kind of stuff became very popular lately also because all of a sudden people were not only say, okay, I'm going to replace this with this new prior. It becomes convex and I can do something. But how far I am from this zero norm, which is the true solution? How big is the price I pay for my approximation? And the bottom line is that there are results in the last few years that basically quantify exactly how much you pay and tells you the condition in which you pay nothing. Okay? You can actually prove that not for any possible problem, but there is a large class of problems for which relaxing the problem's way allows you to get the exact solution. Okay? So this is not in contradiction with the hardness of the problem, because it's not for any problem, but it's for a large class of problems. Okay? And people that contributed to this are Donoho is one of the main people, and then there is a bunch of similar results by Manuel Candes and Terry Tao, Justin Romberg, where they kind of laid down the theory of this kind of stuff. And here I'm really like tipping the iceberg of this. I chose not to give you more detail about this, because basically to go on from this, I have to either get you to some kind of geometric idea, which are kind of abstract, or into computation that would require me to basically introduce context optimization techniques. Okay, so I decided not to do that, and instead to concentrate on another class of methods, which are so-called greedy methods, and they're much easier to explain. And they more or less enjoy the same kind of properties that convex relaxation do have. Okay? So remember that the way we described this was, okay, if you have a least square machinery, I can take all possible subsets of variables and run it, single, double, triplets, and keep on going, and then I find the best. Basically, you cannot do that. If you want to try to approach the problem in a similar way, what can you do, you think? So you try to want to go in this kind of incremental, inclusive direction.
Dynamic programming or 3D?
Simple. I think of something simple. So one thing you can do, instead of, you kind of start the same way. You start to find the first single variable that matters. Okay? And then you basically check whatever is not explained by that variable. And then you start again. And then you start again. And then you start again. The hope is that you're shaving off information by including variables. And then there are all kinds of flavors of doing this, because you can select one variable, then you can put it back in the bunch, or you can keep it out. Okay? And then once you have selected one variable, you have one coefficient. Then you select another variable, you have a second coefficient, and you can decide, should I recompute the solution, yes or no? But the general flavor, and I'm going to show you one instance right now, okay? But the general flavor, before we complicate with the equation, is I look at the first variable which explains my data. It gives me the best prediction in the least square sense. And then I just basically look at the residual, whatever I'm not able to explain, okay? And then I rerun the same procedure on the residual, which is whatever is left out of my prediction, okay? And then I keep on. These kind of methods are called greedy methods or matching pursuit techniques, and that with respect to the convex relaxation approach, they're basically easy to explain. They're elementary from a computational point of view, and that's why I chose to show you this guy. They're kind of slightly annoying to write down, I have to say, but basically conceptually, this is what's going on. So remember that you have this matrix, which is n rows and t columns. Each column is size n. Okay? And then you have the vector of outputs, which is also size n. So what you do is that you basically say, okay, let me see which direction gives me the most explanation of my vector. Okay? This would be this one. And then you can say, okay, if I do use this as the prediction of this yn, what's left? So basically it would be something like this. Then you keep on going. Okay? So the general idea is that you have a notion of residual, and then the first round, the residual is just the vector itself. Okay? Then you find the variable most correlated with the residual. Again, at the first round, you find the variable which is most correlated or most expressive of the output. Then, once you have the variable, you compute the associated solution. You put the index of the variable in your active sets of the variables that you like. Okay? You compute the new residual, which is whatever is left, and then you start again. This clear? Just and wait, okay?
And so for a stopping rule, then you just keep you add in the cost function as well, and just keep doing this until you find something where the total bit plus cost.
So the cost. So it turns out that let's look at this. The only three parameters you have is the number of iterations. Okay, there's nothing else. So you literally just do this. And it turns out that the number of iterations you do is actually related to the number of variables that you're going to include. Okay? So that's actually the regularization parameter. So it's not an explicit penalty. It's not an explicit prior regularization. It's just a procedure itself that by including new variables is going to potentially increase the complexity of the model. So by letting the algorithm run, you're actually including more and more variables and including more complexity. How do you choose it? The same as before. How do you choose k in KNN? How do you choose lambda or sigma in least squares? Cross-validation. Okay? That's the same. So there is, in some sense, I think good question is always, what is the regularization parameter? Once I know it, then I know that I don't know how to choose it, but I can use cross-validation. Okay? The one regularization parameter which is here is, in some sense, the number of iterations here plays the same role of lambda, implicit, not with an explicit penalization, but that's it. Okay? Yes?
When you're doing this, do you have the axes that you're comparing along like predefined, or do you kind of, can you like choose the first one and then just go orthogonal to that afterwards?
They're just this. They're just these guys. So if this is the data matrix, the x's in that picture are really the column of the data matrix. And in fact, I put them orthogonal, they're not. They're just a bunch of vectors. Okay? Typically, you have many. Your situation is that you have something like this, and then this is the yn. Okay, so this is kind of misleading. I just did it for the sake of simplicity. But you have many possible. In this situation, if you think about it, you have all these possible directions, which are many more than n. So it's a very crowded space. You don't have an orthogonal axis. You actually have very crowded or full of directions. And then you look at one, and then look at another one, and you can go on. Okay. And for this to make sense, you kind of have to normalize the column of the matrix, because otherwise the length of the column will tell you something about the size of the coefficient, and you don't want to do that, okay? Okay, so then this is the beautiful, this is actually the code of the whole thing. So don't stare at it yet, just notice how long it is. This is it, okay? This is really the algorithm. You just run this, okay? And the only part where you have to turn on your brain is kind of this, and I have to explain it to you quickly here. The rest, philosophically, is you run the algorithm. This is the selection of the one variable, so let's wait a second to look at it. This is just its inclusion in the active set. This is the update of the W of the solution, and this is the computation of the new residue. Then you start from scratch, okay? So I have to tell you how I select the solution and how I update the coefficient. Does it make sense? And at the end of this, I will have a set, which will be the important one, and a W, which is a vector I can use to make predictions. Oops. Okay. Now, the part that is slightly annoying, this is how they write the selection rule, and it's kind of unrecognizable. But down here, I wrote you very small, because again, this is just a little exercise you can do, and this is the solution. You can show that basically what you're doing here is actually just computing which variables gives you the best least square approximation of the residual. Okay, this expression here is actually the expression of the best approximation of the residual by a single variable. So basically what you do is, I solve the problem with one single variable, and I select the variable that gives me the best possible solution. There is the usual trick here that one thing is fixed, so you can go from a min to a max, okay? So that's what's going on there, nothing else, okay? So don't stare at this too much. This is find me the single solution, give me the best least squares, and this is just one way of writing, okay? And this is how long you have to do, the calculation you have to do to show. If you solve a one-dimensional problem, then you have one variable, one column, and one coefficient, one number, okay? Once you have to update the solution, what you do is that this vk is the coefficient associated to that one variable that you chose. So what you do is that you put, this is just the orthonormal element, so it's the vector of 0 with 1 in the position of the variables that you chose. And so now you put this number in that position, and then you add to the number, to the vector you had before. Okay, so this is a number, this is a vector with 1 in the position of the variable that you chose. You form, this is a typo, you form a long vector, which is going to be all zeros but 1 position, and then you add it to the one you had before. Okay, so this is the simplest flavor of this algorithm, is what is called matching pursuit. It's one example also for forward stage-wise regression, which is an idea that was around in statistics since forever. And it's kind of this forward method. So you forward because you take and include one variable at a time. And this is the way you do it, okay? There's a whole set of things called backward methods where you basically start from the whole thing and shave it off, okay? Forget about this. This doesn't work great, okay? It's the version which is somewhat used to, okay, and I didn't say what you do for the residual, but it's kind of trivial. Once you have the coefficient at that point, you check, you just make your prediction, okay? And then you subtract your prediction to the residual. So the first round, you just have the vector, and then you just subtract your prediction. The second round, you have what's left, and then you keep on subtracting your prediction, okay? There are a bunch of different flavors where the main difference is really the way you update your coefficients. For example, one thing you could do, well, you tell me, what you could do to update the coefficient in a slightly different way, for example?
Do your least squares with the variables in your set.
Yeah, so you have an active set of variables here, and instead of doing this, you just do least squares on that variable, okay? What do you probably gain and what do you lose? So what you gain is that now, suppose that you have variable 1, okay? Then you put variable 2. Maybe you want to change the weight on variable 1 now that you have also variable, and that's exactly what you're doing. You recompute. The problem is that each time, while this solution of this one-dimensional problem is trivial, if at each time you have to increase and build a bigger system, you are solving a bigger and bigger and bigger system, so you pay a price computation, okay? This thing we just mentioned is essentially what is called orthogonal matching pursuit, which can be shown in practice to be much more stable, okay, and works better. And I think today we're going to give you the code for, I don't know, it's both or just the second one, okay, and you can play with it. The key point here is really that by doing this kind of procedure, you're actually approximating the solution of this, okay? And again, there are conditions under which you can prove that there are classes of problems for which the previous procedure gives an exact solution to this problem, okay? So these are all I want to tell you about this. There's really tons of stuff I haven't talked about here. Literally, I think in the last 10 years, there has been an explosion of work in this direction. Okay, so there are tons of stuff. Some of that's a bit more theoretical, some of it a bit more practical. From the theoretical point of view, this drawing here is the one that if you've gone to a talk or those was parts you have seen before, because to some extent I didn't push this perspective because I just want to keep it computational. But behind of this is the idea of how you can solve large classes of undetermined system where you basically have a matrix, a vector of measurements, and a vector you have to look at, which is much longer than the vector of measurements. So there's no hope to solve this problem unless you make assumption. And so basically the assumption we made is that only few of the entries of this vector are different from 0. Okay, that's what we've been doing so far with our methods. And then you can ask, well, clearly, if this number of entries are smaller than the number of this, and I tell you where they are, there's no problem. This becomes an easy problem, right? But I don't tell you where they are. So now the question is, what is the price you pay not knowing where they are, or can you find them? This is another way to say the variable selection problem in this kind of linear algebra set. And basically, the theorem I've been referring somewhat vaguely to tell you that if the columns of this matrix are not too collinear in a precise sense, then you can actually solve the problem. Okay, so you can show that the price of finding the position of these entries is a finite, and it's actually not too bad. Okay? And there is a whole perspective on what I just said that pointed at a kind of new way of looking at sampling theorems beyond the Shannon sampling, which is the one that said if you have a band, you have to go twice that frequency if you want to have exact reconstruction. And basically this new theorem says, what if my band is this big but is almost empty? Do I still have to go twice the frequency, or I can do much better than that? And this is basically saying you can do much better. Okay? It's not exactly as if you just know the position. You basically pay a price of knowing where the location of the frequencies are. And this is basically a whole new idea in sampling theory. There is this whole idea in which basically if you have a vector, you can actually sketch it with a very short vector and still be able to get back to it. And this whole idea of compressed sensing and sketching algorithms and so on and so forth. And this is kind of going out of machine learning into other domain, which kind of do the same stuff, slightly different flavor, and they sometimes talk to each other. But there is also another direction where literally you actually keep on staying in machine learning. And basically, for example, one example is, what if I tell you that rather than having individual variables that are different, I know that in my gene example before, there are a group of genes that are actually associated pathways, and they're actually important. I want to keep them grouped. And what I want to select is not individual genes, but pathways. A pathway is a group of genes that are related to each other. Can I do that? Can I do that if my groups are not overlapping, but can I also do it if there is an overlap? And what if my groups are actually a hierarchy? Okay, I have a big group that's split in other groups. Can I impose this kind of priors? And this is what people are calling structure sparsity. Okay, group lasso. And if you can, in fact, you can make this idea with kernel, you get multiple kernel learning ideas. And this is all somewhat the complication of this, with lots of the tools will remain kind of the same. A more substantial departure from this kind of ideas is when you move from vector to matrices, okay? You go from a vector to a matrix. And so it's kind of all the same, but you would put a matrix here and a matrix here. And the idea here is now what you have to retrieve is not a vector, but it's a matrix. And you can prove that this simple problem allow you to, for example, to describe many vector valued regression problems, for example, and many problems that people call matrix factorization. And so the idea is, again, I have a matrix of sensing or measurement. I have measurements, which are themselves a matrix, but then my unknown is also a matrix. And in this sense, rather than sparsity, oftentimes people think of low rank. They say, if my matrix is big, but it's low rank, so in some sense, the effective degrees of freedom of the matrix is small, can I use ideas related to this to try to recover from much fewer samples than I would guess? And the answer is, again, yes. And the theory is somewhat a direct generalization of the theory. Not so direct, it's a pretty exciting generalization from the theory you have for vectors. Okay? And again, so what I'm showing to you is just the tip of the iceberg. All right. Any question about this? So the take-home message is, it's big. There are a lot of stuff I can tell you about. But the one thing I would like you to remember is, if you have a linear model, and if you want to know which variables are important, you can use this kind of techniques where you greedily start to look at one variable, and then include another one, and then another one. Okay? You can try to use that, try to understand how it works, and then if you're curious, you can use that as an entry point to the whole world of different kind of methods, and find a lot of beautiful math. Okay? That's kind of the hope for this. Yeah, I want to say one thing. The one complaint you didn't say, you didn't make, but I thought you should have done, is linear models, bilinear models. What if my genes are not interacting or are not depending in a linear way to the out? Yeah, right. That's complete nonsense. Why the gene should depend in a linear way to the out? Can't they be polynomial, square? Yes. Do we know how to do it? No. Okay? What we know how to do is basically assume that each gene depends non-linearly to the output, but then just assuming that the genes are linearly interacting with each other. That's kind of easy. They're already pretty rich. But the full, so sparsity with non-parametric, we don't know. Okay? Almost nothing there. There are algorithms that stop working where dimension is bigger than 50. Okay? So it's a big direction. So we do linear models because we don't know how to do anything else, and because it's good in a lot of different situations. Okay. So I don't know what to do with this. over this. How many of you know what PCA is? Right, so we just go to lunch. So I just give you a quick presentation of PCA, mostly because I liked it, and when I put it together, it was slightly different from the one I found, and I found it was instructive to do other stuff. Okay. We have to go exploding. So what's PCA? You have data, high dimensional. You don't have labels now. Different game. You don't know faces or not faces, just stuff. In this case, images of numbers. And you want to basically put down the dimension. Throw down the dimension from whatever it is to much low. Why? Bunch of different reasons. One is, for example, you want to look at the data. You want to take three-dimensional description of the data rather than, say, 120-dimensional. And you want to plot the digits. And you would like to see that some digits are here, some other are here, and so on and so forth. What kind of shape they have. Okay? Are they all mixed or they're all nicely separated? How do you do that? Here's the problem of dimensionality reduction. It basically says, if you give me vectors of size D, I want to do a map that put them down to size K, where K is much smaller than D. Okay? This is my question now. There are no labels. Okay? I'm going to do this on the basis of a bunch of points. The easy case is, how about one dimension? I want to project in one dimension. I give you a bunch of vectors, and you want to project them in one dimension. What do you think is a good idea? What would be a reasonable idea to find? And let's also make the case that we are fine with linear projections. Okay, we want to find a linear projection. We have a bunch of vectors. We want to linearly project them down in just one dimension. And I want to find the one dimension which is best. What would you say? Maximize the variance. That's one. Okay. What does it mean? You take all the vectors, you project them down in every possible direction. You look at how they are spread out. If they're spread out a lot, you're happy. Okay? And you choose that direction. What else? One point of view is to say, if you give me vectors and you don't tell me anything else, and I project them down, I might want to be able to reconstruct them, okay? To describe each vector using the least possible amount of information. Variance is one way, but one can ask why variance, okay? You can say, maybe I just want to keep as much information about this one vector as I can. Make sense? So the way you would do it is basically saying, pick a vector, okay? Now pick a unit vector. So this is the vector I want to compress. This is the unit vector. And what I'm going to do is project it in one dimension, okay? I just go in one direction W, and then I check how much I'm saving and how much I'm losing. I computed the difference between the vector I started from and its one-dimensional projection. It make sense? So it's literally the picture I showed you before. You take a vector, you project it in one direction, and you check what's left. Okay? Only here, the vector are one input vector, and it's one-dimensional projection. Does it make sense? I mean, it's this time I'm not sure it should make sense, but this is just a one-dimensional projection on a unit vector. So you take this X, you project it here, you get a number. This is the length of this one-dimensional direction, and then you check how far you are from the original vector. Okay? So one idea to find this one-dimensional direction. So this is the one-dimensional projection, okay? Linear projection. So the idea is, I want to do this for all the points at once, and I want to find the direction which, on average, is the best for all the points. It allows me to get the best reconstruction. Yeah?
What's the difference between this and finding maximum variance?
No.
Okay.
This is just a geometric point of view. They're the same. Okay? And that's what's coming in one. It's just exactly the same, just a different point of view. Okay? So, this thing here is just a sphere. It's just unit vectors, nothing else. I have to restrict myself to unit vectors, otherwise I have this scaling to somewhat mix up things. One thing is about computation, one thing is about statistics, okay? So statistics is exactly what you just said. If you do nothing but taking this square, expanding it, just notice that because these are unit vectors, some nice things happen. No, actually, yes, less than that, because this, when you do the mixed product of these two, it simplifies with the square of this. And then you can go from this min to this max, okay? And now when you look at these max, you see that if these variables are centered, otherwise you do have to add the centering, maximizing this is actually maximizing exactly what he said. Just look at one direction, which gives the maximum variance. But this is equivalent. The one direction gives the best reconstruction. The thing which is not that obvious, okay? Why reconstruction and variance? It's here, so it's quite convincing. It's not obvious that these two motions should be directly related to me. And this is the one picture, okay? So basically, what is the principal component? Well, it's this direction. Why? Because in this perspective, if I project there, this is the kind of spread I have, okay? The thing which is kind of cute, I think, is the computations, okay? Now, let's stick to this formulation. And basically, what you can do is that you can just expand here. It's very simple. So you just take this square, you just write it down explicitly, you do symmetry, you get this, and then you use linearity to plug the summation in, and then you get the quadratic form at W transpose times this matrix W, okay? This matrix here is just the second moment or covariance of the data. And so it turns out that you can rewrite this maximization problem as the problem find the maximum of this quadratic form under the constraint that you have unit vectors, okay? And either you remember, or you can just use Lagrange's theorem to prove that the solution of this problem is just the maximum eigenvector of the matrix Cn, okay? I think the beauty of this is that there's nothing else to know about CA, okay? So you start by asking yourself what is the best one-dimensional projection. You write it down. You just pass to the max problem, and it takes one line. Just do this one calculation, and it pass to this quadratic form. And then that's it for the computation, because either you pick it up from a book or you prove it in one line. This is the solution. The one direction of this problem is the maximum eigenvector of the matrix of the covariance matrix of the data. Okay? And so for k equal to 1, this gives you, at least in this max variance reconstruction framework, the solution to the problem. Okay? What about k equal 2? With a little effort, what you can show is that basically using the same idea, if you don't make any assumption on the second vector, you say, okay, I found the first vector this way, I just want to find another one. It's a mess. But if you ask the other vector to be orthogonal to the first one, then basically you get to this problem, and it turns out that the solution to this problem is the second eigenvector of the covariance matrix. You just keep on going. Okay? And you can even do, of course, you can go from k equal to 2, k equal to 3, and so on and so forth. So the whole problem of dimensionality reduction in this case just reduces to find the eigenvector of this matrix. Notice that there's a big difference with the variable selection problem, okay? The eigenvector of this matrix is going to be linear combination of the vectors. But you're answering, in both cases, you're reducing the dimensionality of the problem, okay? But in this case, what you find is a mixture of variables. Suppose you go to the doctor before, okay, and you use this. He's going to ask you, okay, nice. You can show me the patients in low dimension. Which variables are important? Which genes characterize these patients? You don't know. Because the first principal component, this guy, might as well be a combination of all the genes described in patients. Okay? So it's very different. And this motivated extension of this try to find so-called sparse DCA that would give you sparse eigenvectors and so on and so forth. Because clearly, you cannot just say, oh, let me go back to the other method, because you need labels for the other method, okay? Whereas all here is unsupervised. And this is indeed one possible direction of extension. There are many, many, many others. One direction is basically saying, I keep the idea of going down linearly, project down linearly, but instead of reconstructing or maximizing variance, I say that what I want to do is to preserve, at least locally, the distance among my points. I have vectors in high dimension. I believe that to some extent, distance do matter, and they're reliable, and I want to preserve them when I project them down. Okay? And this is a classical question, and one possible answer to this is the one given by the Johnson-Lindner-Strauss lemma, that says that if you take a random matrix, for example, a matrix with Bernoulli entries or normal Gaussian entries, then you can achieve this with high probability. You can project down the data from dimension D to dimension K that depends on the number of points and number of dimensions so that you preserve the distance at this local. Not only that, if you keep the same idea of projecting down in such a way to preserve distances, but you drop the linearity assumption, okay, you don't ask this map to be linear anymore, pretty quickly you get into ideas related to manifold learning. And idea stuff like Laplacian eigenmaps, Hessian eigenmaps, a lot of eigenmap stuff, fusion maps, and so on and so forth. And basically the idea there is that you try to, given the data that might lie on something which is curvy, you try to find a nonlinear map that straightens this out, so that the distance between these 2 points should not be preserved, but the distance between these 2 points should be preserved. Okay? And you allow yourself to do it in a nonlinear way. From a practical perspective, a lot of this is easy because it's just a random matrix and you apply it. A lot of these methods are related essentially to looking at this and doing a kernel version of this. Okay? Most of the manifold learning method from a computational point of view just reduces to look at this and basically say, this is X transpose X. I want to do X transpose. And then I use properties of the SVD. Okay? That's more or less where it is. And again, the list of things you can do just building on this, going either, so you can do a lot of things where you start from PCA and you go in the direction of sparsity. You can do a lot of things you start from PCA and linear using kernels, somewhat mixing the idea we've seen before. The thing to remember is that you don't get variable selection, but you do reduce the dimensionality in an unsupervised. Okay? And that's more or less what I wanted to say. Again, the purpose of this was mostly just giving you, if you're on a desert island and to bring 5 machine learning algorithms with you, which one would you pick? Okay? And I would say these are basically what I would pick. I might take kernel, k-means just in case. I didn't have the time to tell you about it. I would say t-squares, linear, nonlinear, variable selection, PCA, nearest neighbor should be selecting the island. So again, if you are new to this should have been kind of confusing, but hopefully giving you enough pointers that today you can sit down and try to use some of this. If you know some of this, if you've already seen this, hopefully you'll get enough pointer to kind of see the overall picture and look for further development. Okay? And I'll be around anyway, so you can ask me all kinds of questions. So if you have any questions, right, you can go for lunch. Okay. Yeah.
I need to ask about matching pursuits. You said that one of the limitations is that it's linear.
That it's no, that you have to solve a linear. So if you do a matching, so the standard matching pursuit, at each step you just solve a one-dimensional problem and you update it. And that's okay, but it turns out to be unstable because basically there is not enough coupling between the variables you are selecting intuitively. The orthogonal matching pursuit is the one where whenever you select new variables, you add it to your set and you recompute the solution. That one is much more stable, but each time you introduce a variable, you have to solve a linear system. And this costs you whatever it is, p cube. Okay? So if the variables that matter are 5, perfect. It's much better than anything else. If you start from 1, 2, 3, 4, 5 linear system, you're good. But if by any chance you start row systems bigger, you have as many linear systems, so growing much bigger. So that's the main limitation. In practice, I would say it seems that in hard problem, the convex relaxation approach seems to be somewhat more stable. But I wouldn't, I would personally not make a huge statement. Yeah.
Solving a bigger linear system each time, but you might be able to reuse the partial solution to the last. That might be a closed solution.
Yeah. So I have to say again, for some reason, myself particularly, I've been focusing a lot on the convex relaxation approach, also because there is some very nice optimization theory. There's been a lot of interest in this kind of first order methods where you basically put the gradient of the squares and then you project it down according to some rule that depends on the one penalty. In fact, when you have to start thinking about choosing the parameters and looking at the level of sparsity, to some extent the fact that automatic this iterative warm-up, built-in property is nice. But I'm not aware of as many, I should look more into it. I think lately there has been some things in the direction you're saying, but for a while people didn't look too much in. I think now that you have big data and you have to choose lambda, and you cannot just run it many times, matching pursuit will become more and more interesting.